Looking forward to your presentation, and we're ready to go.
Hello and welcome. My name is Volker, and I'm very happy to have the opportunity to talk with you today about continuous and intermittent direct electrochemical lithium extraction. Our research team is located at the German-French border in the charming city of Saarbrücken. At the Leibniz Institute for New Materials, we do material synthesis, electrode fabrication, and battery and water research. At the University of Saarland, we're exploring soft materials, especially polymers. And finally, at SARIN, the Saarland Center for Energy Materials and Sustainability, we're networking with the other professors and research groups on campus to a more sustainable future. Our team brings together material science and energy materials to develop novel materials and processes for energy storage, water remediation, and as a very big focus these days, battery recycling and circularity as well. When we look at the current large-scale extraction methods for lithium, we see that they fall into one of two categories. On the one hand, we have conventional mining activities. Depending on which system you use and the geological details, 1 ton of lithium carbonate from spodumene ore may come down to 20 tons CO2 emission and 77 cubic meters freshwater consumption. This accounts for around 60% of the globally mined lithium. The rest of the 100%, about 40%, comes from lithium concentrate via brine. Depending on the technology that you apply and the geological setting, the settings will allow CO2 and freshwater consumption to be much smaller, around 3 tons CO2 and about up to 33 cubic meters of freshwater. However, with an ever-increasing amount of lithium being needed for electric cars, large-scale energy storage, mobile computing, we are looking more and more into alternative reservoirs. One such alternative reservoir is battery recycling, including scrap, but also other aqueous-based media. When we compare the about 14 million tons of lithium ore resources on land with the 230 gigatons dissolved, admittedly at low concentrations, in the Earth's oceans, we see the large reservoir of lithium that we could, in principle, technologically tap into to overcome lithium shortage globally. One of the challenges is, of course, the very dilute amount of lithium in the Earth's oceans, which is about 0.2 milligrams per liter. There is, of course, a big rush towards lithium, and the more obvious choices for water resources, of course, pertain to hydrothermal or brine, where 200 or up to 2000 milligrams liter lithium can be found. But regardless if your aqueous body has higher or lower concentrations of lithium, we mandate an energy efficient and effective way of extracting it with high ion specificity, because those reservoirs very often occur in competition with many other cations in specific. This mandates direct lithium extraction or DLE technologies. Specifically for Germany, last year there was an interesting case study that compared all the large-scale gigafactories being built in my home region of Saarland. This is supposed to be SVOLT in Oberham and ACC in Kaiserslautern. When we put all of those together and compare especially hydrothermal water or geothermal water resources In the lithium context, the concentrations of lithium multiplied by the flow rate. We estimate that up to 20%, specifically up to 19% of the annual lithium-ion battery production currently being set up could be met by German domestic lithium. And considering that Germany is not very rich in geothermal settings except from certain hotspots, especially in the Oberrhein area, we see that tapping into regional lithium availabilities is a globally applicable and very attractive perspective. In Saarland, we also have, in addition to hydrothermal waters elsewhere, the occurrence of mine water. There, the lithium concentration is not as high as in many hydrothermals, of around 2 milligrams lithium per liter. However, the flow rate with 444 liters per second is rather high compared to other settings. Direct lithium extraction tries to bypass the way from brine to lithium carbonate by going directly in extractive methodologies to up-concentrate lithium and to eliminate the uptake or reduce the uptake of other ions. This shortcut is, of course, something that is heavily explored by a lot of scientists around the world. Typically, people use adsorption techniques, where lithium adsorbs onto a sorbent and is removed by a strip solution. Ion exchange processes, where lithium cations are chemisorbed onto a solid ion exchange material and swapped for another cation. Or solvent extraction, where liquid phase sorption or ion exchange occur. However, as exemplified here by Busy Day in London, electrochemistry is a very attractive way of guiding the flow of ions and telling ions to go to a certain direction. An analogy here with the traffic lights that are also electric impulses telling people, solvent molecules, cations, the buses, and anions, the cars, to go to a certain direction at a certain time. For a long time, capacitive deionization and decyanation batteries have employed blind, non-selective means, where an electrified surface is only meant to immobilize counterions, that is, ions with opposite charge, and ion exchange processes pertain to electrolyte compensation reactions. The universal applicability of BDI and CDI technologies is also revealed when we open us up towards other ions, not just sodium and chloride or other inorganic molecules, but also to the range of organics. For example, with our colleagues at the Umweltforschungszentrum in Leipzig, we're exploring the organic pollutant removal by applying ion electrosorption on modified carbon materials. In collaboration with our colleague, Professor Chun-Soo Kim, we also explore not the removal of something undesirable, but the recovery of something desirable, like TMAH, which is recovered from wastewater from the semiconductor industry very effectively using a modified redox flow desalination setup. Indeed, I like to think of ion selectivity or ion processes always in regards to the good, the bad, and the ugly. To uptake ions and extract them that are useful, specifically like lithium, cobalt, and nickel in the context of battery research. The ones that are ugly, like pollutants, lead, phosphate, arsenic, and the useless, the bad ones, that are just ions that we want to get rid of, that are neither good or bad, just a way of high effective ion separation. So we embrace the full spectrum of electrochemical processes ranging from electrosorption, which usually has a low selectivity, towards Faradaic processes, charge transfer processes across the fluid-solid interface, ranging from surface redox, intercalation, conversion, alloying, and redox electrolytes. We can even go full way into catalysis, electrocatalytic reactions occurring at fluid-solid interfaces to provide the charge that we need to compensate with ions, the motor that drives the ion uptake and release. Knowing especially the ion selectivity of certain of those processes, like conversion reactions, some alloying reactions, and ion intercalation processes, we can use and capitalize off of such electrochemical processes with a target of specific ion recovery and separation, and none of them elements is more attractive to explore in this regard than lithium. Ion selectivity, as mentioned before when I was talking about the plethora of different electrochemical processes, can be enabled by different mechanisms, different settings. The easiest one is during ion electrosorption, where we have different sized pores in an open porous network, like activated carbon, carbon-derived carbons, or other nanopores that you have formed in a material that is conductive. There we see that the ion uptake indeed depends on the matching of ion size and pore size. And we see that, for example, cesium and potassium for small pores can reach high uptake capacities, whereas lithium, magnesium, calcium remain small. Now, taking up ions that you don't want to have and leaving behind the one that is more desirable, like lithium, is one possibility of inverted selectivity. However, the selectivity values during ion electrosorption in nanoporous media is usually pretty limited. In our experience, something like 1 to 10 is a higher value that you can reach this way. An alternative to that is a more confined two-dimensional environment, like MXene as shown here, where you separate by kinetics. This, of course, is also applicable to ion electrosorption in nanoporous media. Here you wait for ion-ion exchange processes to occur within a confined space, be it a pore or an interlayer space, just the same. Here we also have seen that here normalized versus lithium, selectivity values usually are not that high. Typically 1 to 3, 1 to 4 are higher values that we can reach that way. Much higher selectivities in the values of thousands, tens of thousands, or even more are possible by using ion separation by actual nano confinement on a crystallographic way, like exemplified here for lithium iron phosphate, but also for other materials like from the Lisicon family. Indeed, lithium iron phosphate is not just a very exciting battery material on the verge of replacing for many electric cars the established nickel and cobalt containing cathodes, but it's also a very interesting material from an electrochemical point of view. When exposed to single salt systems, we see the very large current response when immersed in lithium chloride compared to sodium, magnesium, calcium chloride. But single salt systems don't tell you much about selectivity. Indeed, 10 years ago, in a collaboration with our friends in Israel, Doron Auerbach and Mikhail Levy, we had already explored the lithium selectivity of lithium iron phosphate with electrochemical quartz microbalance experimentations, where we had a solution of lithium and sodium sulfate, and we saw a perfect fit where the trace of the potential versus the concentration fitted an almost exclusive pattern of the concentration of lithium. Only when starved for lithium, then sodium was also uptaken. It is thereby a very selective material indeed. The crystal structure of lithium iron phosphate with the unique confined space for lithium really favors lithium size and charge-wise over other cations. In experiments, it's not surprising to have experimental data like the one that you see here, where we flow sodium and lithium containing solutions in a mixed system, but only detect the uptake and release of lithium during electrochemical cycling of lithium iron phosphate. Indeed, the extraction capacity is about 20 milligrams lithium per 1 gram of LFP per cycle. This comes down to an energy consumption of around 4 watt-hours per mole of lithium ions. And this includes a modest estimate for pumping energy. However, if you really want to extract more precise data, a much larger prototype will need to be developed and built to more realistically benchmark the energy uptakes. That also pertains to costs. In our small-scale system, we had around 1,565 euros per kilogram of lithium chloride, but scalable material availability, costs, and other effects need to be considered for much larger applications accordingly. One reason why a lot of scientists don't like to work with LFP and prefer lithium manganese oxide or other oxide systems is the instability of LFP in oxygen-containing aqueous electrolytes. One possibility to overcome that limitation is by bubbling, removing the dissolved oxygen, and we reach much higher capacity retentions of around 100 cycles. However, this is very often not practical because it involves a lot of water treatment for deaeration. A more practical approach was demonstrated by us that applying a carbon coating around the LFP particles gives also very stable performance and higher capacity retention over continuous cycling, specifically for lithium extraction. There are different ways of capitalizing off of the lithium selectivity of lithium iron phosphate, for example. You can pair lithium iron phosphate with a chloride electrode, like silver-silver chloride redox couple or other systems, whereas by intermittent operation of charging and discharging, you uptake and selectively release lithium and chloride into solutions. This mandates, however, valves that change the feed solution to the recovery or recycling solution between the cycles. An alternative system that also intermittently in a swinging chair or rocking chair geometry operates uses lithiated and delithiated LFP separated by one anion exchange membrane. There you uptake and release lithium in channel 1 and channel 2, and chloride ions can pass through the anion exchange membrane for compensation. This generates during the charging process an increase in ion concentration in channel 2, whereas in the discharging process, you uptake and release in a mirror image. So channel 1 becomes the one that gets enriched. We explore this, for example, in the project Merlin, kindly funded by the RAG Foundation, where we specifically target the mine water of Saarland as a case study. Here you see the map of Saarland, and the cluster of old mines that is around Saarbrücken, Kamphausen, Reden, Victoria, Luisenthal, and Ensdorf. However, the concentration is very small, 10 times higher than in the Earth's oceans, but still very rich in competing ions and low compared to hydrothermal settings. However, it is also possible to have the electrochemical lithium extraction combined with a continuous process. Here, in all crudeness of the experimental setup that we explored in our laboratory, you see an electrochemical cell with multiple channels that on one hand, we have the lithium recovery solution that is pumped through the system continuously. We have a feed solution that is also pumped continuously through the setup that contains the lithium initially. We also have in that setup either flow electrodes or for other setups, process where we have redox flow battery chemistry circulating, separate side chambers that uptake and release the lithium containing solution in a controlled fashion. So we know that either using slurry electrodes or redox flow, redox electrolyte systems that is, we can transition desalination to continuous desalination and ion separation towards continuous separation. We have explored in our laboratory a great number of different setups. Earlier, I briefly mentioned the redox flow battery system that Professor Junsu Kim and us explored for organic ion recovery. In that setup, we used a pair of two Lisicon, lithium superionic conductor electrodes, ceramic, that separated the redox catholyte and the redox anolyte. We also had to separate the seawater from the recovery solution, a simple polymer-based anion exchange membrane, AEM. The anion exchange membrane allowed the lithium not, but the chloride ions to move from the seawater into the recovery solution. Lithium, and in this case only lithium because of the extreme high selectivity of Lisicon towards just lithium, was uptaken into the redox catholyte to balance the charge imbalance triggered by the redox reaction. The redox catholyte was then, over a reservoir, pumped into the anolyte compartment, where the reaction there released the lithium plus through the Lisicon membrane into the recovery solution. The scheme now you just need to complete by having the redox anolyte then flow into the redox catholyte through a reservoir again, and you close the loop. This allows you, just like shown in the photograph in the small video from before from the setup, to have a continuous inflow, for example, of seawater, mine water, or as we explore, hydrometallurgically grade dissolved batteries, and to have a separated continuous recovery solution circulating. This process you keep up as long as you want to reach a certain concentration in the recovery, and you can circulate and recover the seawater or having in a one-way street only, depending on your setup. In our system, we did some calculations and saw that for a 1 square meter lithium extraction redox flow battery setup, we would have an equivalent of around 18 kilograms of lithium carbonate per year recovered lithium from seawater. These numbers, of course, will greatly vary depending on the setup and system that you use. And in our system, specifically for the small scale, we used rather thick Lisicon membranes that slowed down the process significantly. More advanced membranes will yield a much more preferable uptake capacity and rate. And why is that so important also in the context of lithium-ion battery recycling? It is very important because the hydrometallurgical recovery plays a key role in several aspects of black mass treatment. And when we compare the currently available tons capacities of lithium recycling in Europe, it's a joke in terms of total capacity compared to the production capacities. So when we compare production of lithium-ion batteries in the megatons per year and the recycling capacities in the kilotons a year range, we see that the law mandate by European Union and many other countries in the world towards more and more recycling, for example, by 2035, new batteries need to have a fixed amount of recycled lithium in each cell. And the total lithium by 2030 that needs to be recycled will be around 70%. Other countries have even more ambitious goals. So really think that hydrometallurgical, in addition to sourcing lithium from hydrothermal or other aqueous media, can be enabling technology when enhanced by electrochemical direct lithium extraction. I'm sure I will be able to show you more results on our battery electrochemical recycling activities. We haven't published the results completely yet, so I hope you will understand that today I have to remain a little bit more vague on this topic. So how does it compare then when we see the production from spodumene ore, the mining activities and the brine activities? Well, we really think that EDLE, electrochemical direct lithium extraction, will play and can play also from a CO2 and energy cost point of view, a very attractive role in the plethora of electrochemical and chemical and physical extraction methodologies for lithium. The exact values, however, will be a challenge to establish in rigorous techno-economic evaluations yet to come. As a conclusion, we see that the electrochemical direct lithium extraction is an interesting method that by definition does not consume chemicals. It quote unquote only needs electricity, and that allows you to harvest renewable energies fueled into the extraction process. We've seen the process can be both fully continuous or intermittent, depending if you adopt a more conventional desalination battery setup or a desalination flow battery concept. We see that electrochemical direct lithium extraction is compatible with natural aqueous lithium-ion reservoirs. And we also have seen in our own experiments that it's also compatible with hydrometallurgical lithium-ion battery recycling. We are very much looking forward for partners to advance the technological readiness level and address scalability. Thank you very much for your attention. I also acknowledge, of course, the great support from my team, current and past, the great network of collaborators. And once again, thank you so much for your kind attention. I'm looking forward to your questions.
Professor Presser, for this for delivering this invited talk where you focus on let's say ion management, as you call it, and also sharing your endeavors in taking shortcuts in this particular case on lithium extraction. There's time for questions. I first look here at the audience present in the room. Yes, over there. You can clearly hear us, Volker? Yes.
I can hear you clearly. Okay. Yes.
Thank you. Thank you very much, Professor Presser. My question is about you using the least count as the separator.
Yes.
Because you using the seawater, but the concentration is extremely low, right? So based on this, what should be the current density or current you can apply when you're using this kind of device? Because it will be the rate determining step for this. Is that right?
It's one of the rate limiting steps. It also pertains a little bit to flow rate. The more important one is current, as you correctly mentioned. And of course, the lithium concentration is important to be considered. With Volker, it works well. We have seen good performance in that system. With higher concentration, it depends what other ions are in the system and the pH value, especially for hydrometallurgical solutions where we operate in very acidic media. You need to modify the lexicon. So it's not just applying a higher current, but also how to prevent the corrosion of the system. And you cannot go too high in current for your system, otherwise you suffer from very low energy efficiency. It depends on the thickness of the membranes. We have very often rather thick membranes because of the setup that we're using. But for thin membranes, you can draw inspiration for the currents to use from redox flow battery desalination systems, and just consider that the ion flux is much smaller and much slower compared to polymeric systems. But yes, be careful with adjusting the current, but go and max out the current that you apply, that you can optimize the performance. It depends also on your size. If you have 10 by 10 or 5 by 5 centimeters, we envision much larger systems, but yeah. But thank you so much for your question.
Okay, Louis here, the chairman back again. So thank you for making this warning. Be careful when playing with the current. I also be careful when making lexicon membranes less thick, right? In terms of being fragile. So what ideas do you have to go into that direction? Because you say you use rather thick membranes. I don't know how thick. You tell us it has to do with the current setup. It also may have to do with them being fragile.
Both is very true. So the current setup that we're using, we're having discs of like 4 or 5 centimeters maximum. Usually we even use much smaller ones of 2 centimeters and smaller. So with that, you need high frustration tolerance level when starting this kind of research, unfortunately. So a big warning to students starting on it. You need to be careful. You will run through a couple of those membranes by simply nicking and breaking them, but making polymer lexicon, or in for our other research, and polymer nasicon composite electrodes, that helps a lot with having both mechanical strength preserved and still the high selectivity of the ceramic membrane enabled.
Okay, thank you for that clarification. In view of Julio, there's a final question, and then we close this this discussion. Julio,
one quick question. Very nice talk, and I'm curious about the stability, or how to improve the stability of the LFP. Could you explain a little bit more what you did there?
To modify the stability or to test the stability?
To improve the stability of the LFP.
Yes. So first we explored, of course, the big baddie for a lot of BDI system is dissolved oxygen. It also is a detriment to regular CDI. So one thing we just did, the electrolyte on purpose with inert gas to remove dissolved oxygen, and on the other hand, to bubble it with oxygen to really make sure it's highly saturated, and compare the results accordingly. For the modification of the LFP, we drew inspiration from what the battery industry has been doing for many years. Embedding. Most commercial LFP that you buy has a little bit of carbon around, better conductivity, better resistance, wonderful interfacial resistance lowered. So we just on purpose increased by a larger degree the amount of carbon wrapping around the LFP particles, and thereby we strongly enhance the stability of the system. But it will still depend if you are highly acidic or highly basic. What are the other ions? Calcium, for example, is a big problem for the LFP when you want to recover lithium. But carbon coating helps a lot. Be careful, use lower pyrolysis temperatures for that, because you don't want dense graphite to form around the LFP granules, but just disordered porous carbon that allows you to still transfer lithium more or less at the same rate as bare LFP.
Thank you.
Okay, thank you.
If there's more questions, just shoot me an email and I'm happy to respond. Sorry for not being here today with you folks, but thank you so much for having me regardless.
Okay, thank you.